buttons on. Hello. What is this? Let me see. Okay, sorry. I have to always discover and rediscover some of the buttons that are on my YouTube live whenever I do go live. Okay, so I think I follow. Actually, give me 1 second. Oh, I see. Okay, that's the button to turn off the camera. Okay, so good evening, good night, good afternoon, good morning, everybody. If you're joining us, I do hope that many of you will be joining us tonight. And if you see this as a video upload later on, well, welcome so much. Thank you so much for joining. And please do leave us some comments, like, share, subscribe. As usual, you might hear Baji Baba here. He has been circling me for a little bit. As soon as I got set up for this live, he came behind me and he has been getting some pets and some love. They missed me very much when I was at the gym, so here we are. They got their dinners and snacks and all of that, loves and all of that, and even some playtime. And here we are now, we're live, and I've got this excellent book with me. And I have a topic picked out for tonight that we will talk and discuss. And I do hope that many of you will be joining, my old and new friends. If you're new to the channel, please do join and say hi. Can't wait to see many of you that are both old and new. And please do double tap and give us some likes, give us some subscribes. Really appreciate it. And before I forget, let me share the live. So anyways, that was my little beginning spiel. Usually what happens during these videos is that I say hi to everybody. Depending on if people are joining, I might say hi to each of the usernames and people that are joining. And so if you have any comments, any messages, anything you want to share, go for it. I usually read them and whatnot towards the beginning of the live. And then I dive into the topic, which for tonight is going to be pulsars. Also, if someone could mention in the chat at some point when people are joining how the audio is and if everything is working good, that would be most excellent as well. But tonight's topic is pulsars. Oh, I see it on my laptop on this side as well, which means that I think the live is now living. And so we will get into it from this book called Modern Astrophysics, an introduction to modern astrophysics, right here with me. This is the second edition of this book. So this is quite a heavy book, but I like it. It has a lot of things. It really does a good job of covering a lot of different topics from modern astrophysics. So it's not sort of irrelevant. It's very relevant types of topics are in here. I mean, nothing is irrelevant, but what I mean to say is astrophysics, astronomy is quite old, and modern astrophysics is something that is not always treated by everybody, because sort of the topics that have come up in the last century or so, or in the last decades, is something a little bit different from what we were able to what we used to be able to do back in the day with astronomy and things like that. So I think it's good to look at the topics and look at a book that treats the modern things in a more modern way with the current techniques and whatnot. And so the information should be a bit more current and relevant. But also I will mention that this book, the second edition of this Introduction to Modern Astrophysics, is from my undergraduate days. So I remember taking a special course in astrophysics as an undergrad, even though I studied it further in grad school. In undergrad, not everybody has to necessarily take an astrophysics class. It was a special topics class taught by my very favorite professor, one of my favorite professors at NC State, Dr. Carla Froelich. And she taught this, and so I took it, and she was also my undergraduate research advisor in astrophysics. And so it all kind of came together, and I went on to pursue particle astrophysics in grad school. But I actually didn't know that that's what I would be pursuing. So it turns out whatever I learned from this class and from my undergraduate research helped with grad school, but actually, you never know exactly what will happen in the future. But so this book is not so new. It's more current. Everything that we touch upon from this book should be pretty current, but just keep in mind that things do get updated over the years. And so anything from the past decade or so might be something that still needs to be updated in this edition. So once again, this is an introduction to modern astrophysics, the second edition of that by Bradley W. Carroll and Dale A. Osley. So this is, in short, we call this Carroll and Osley. It's very well known in astrophysics in the field. These authors have done a great job, very comprehensive book, and there's lots and lots of topics. So now, some of the time that we have covered certain topics in astronomy and astrophysics, we have actually referred to this book. I remember there was a time when I was asked about the sun during one of these lives. And believe it or not, I'm actually not the best person to talk about the sun because I mean, you know, I guess embarrassingly so, I know not much about our sun. The sun as an astronomy topic is not something that I studied very deeply. My background, my studies were very much focused on particle astrophysics and doing astrophysics with various messengers that are not light, meaning usually that those were extragalactic types of astrophysics. So not even this galaxy. So I am probably not the person. I know more about the galaxy now because I've studied it since then, but my PhD actually is for extragalactic astrophysics. So that's why, you know, hello everybody. I'm gonna say hi to you in just a second, but yeah, that's why the sun, which is even more local than our galaxy, is something that I didn't know a lot about. All of that is to say that this book actually has a very comprehensive coverage on the sun. So if you're interested, we can talk about our sun from this book. Like I definitely have to I definitely have to refer to a book like this if you ever ask me questions about our sun and whatnot. About our galaxy, I can manage from the other book that we have also used a lot, which is called Foundations of, in fact, where is it? Oh, there, it's over there. I won't get up. It's called, so everybody, can you please double tap and give us some likes? Thank you so much. The other book is called Foundations of Astrophysics, which is, I believe, the majors astronomy and astrophysics class that's taught in the astronomy department of various schools. And that book has also been a lifesaver for me, and a lot of the topics like our galaxy and various different galaxies, and especially, you know, growing up on astronomy, astrophysics, what I mean by growing up is when I was taking the coursework myself in those topics, I didn't cover the galaxy much as somebody who was in the Department of Physics. So it was nice to then start collaborating with the Department of Astronomy, where I learned more things that are more astronomy-y versus physics, if you know what I mean. So anyways, I'll continue all that. Let me say hi to everybody. Sorry about the delay in saying hi, everybody. Let me scroll and say hi to you. Biggest fan says hi. Hello. Daily motivation, how are you? Can you tell my baby bro happy birthday? Happy birthday to the baby brother of biggest fan. And sorry if you're not here, then you missed it. But if you see this later on, happy birthday. The cool guy says, wow, the prettiest woman on YouTube. Oh, thank you. Biggest fan says, we're watching. Oh, thank you so much. And happy birthday. Pranay says, Audrey, you're wearing full makeup. By the way, you're looking very beautiful today. Wish I could go on a, oh my gosh. Well, thank you so much. This is, I did put some lip gloss on. I don't know about the full makeup, but thank you. Skeletor RA says, hello, hi. Jorge says, Buena noches, señorita, mother of cats. Enjoy your lecture. You're so intelligent. Have a great night. Thank you so much, Jorge. How are you doing? Please do stay on if you can. And please do double tap the live. I feel like if people could give us some likes and subscribes, that would be most excellent. But yeah, so let me share the live from my phone and also my laptop. Hi, Yakov. Yakov is saying hello. How are you guys? So anyways, I was telling you about how even when you go to school for a topic, not every topic is something that you'll necessarily learn about. So galaxies is something that I did not learn about a lot when I was myself in school, but more recently I started to learn more about it. And all of these books that I reference a lot on the channel are those books that I learn these topics from. The sun is something I still don't know a lot about. And tonight's topic, thank goodness, is pulsars and neutron stars, which I do know a little bit more about. So pretty much if the object or the event is more extreme, then I might know some things about it. If it's something local like the sun, or even worse, if it's one of the planets, I might not know much about it, and I'd have to reference the books. I do have quite a few books that cover the planets and all of this other stuff. And also on this channel, if you're somebody who really wants to, say, hear about Mars or other planets, we actually did a whole series on that. So even though that's not my expertise, we did cover the planets from the proper books and sources, and you will find actually quite an in-depth discussion on all those planets in our solar system in previous lives. So I always encourage, go and check the videos that are already posted under the live tab of the channel. You will find a lot more information there. Planets, galaxies, sun, stars, supernovae, physics, cosmology, all of that is in there, okay? Okay, so now what am I doing? I wanted to get my live monitor up so I can make sure that the settings are good, and then we'll dive into the topic. And if anyone else wants to say hi in the chat, please do feel free. I don't see too many of my old friends here. Pranay, are you still here? Skeletor, how are you? Please do continue to say stuff in the chat. That tells me that you're still here. And if you're one of my old friends, then please do say hi. Lovely to see you, as always. Okay. So YouTube always changes up the live settings on me. And so I have to make sure that the settings are actually set. And whatnot. Thank you for liking and sending the emojis and whatnot. And I will say that, and I will, I tried to send myself a message and it did not work. Okay. That's okay, that's okay, I suppose. Okay, let me also share it, because I never shared it. And then I will get into the pulsars topic. So, by the way, some of you guys, Jorge is saying, did you have a stress relief walk today? Oh my gosh, how did you know? Yes, I did. It was a walk to catch my bus, actually, and then I had to walk more because I caught the wrong bus because I missed the right bus, and then I went to the gym and I did swimming, and then I did stress relief, sauna, hot tub, showering. So I actually did all that for stress relief tonight. So indeed, you were correct. Thank you for remembering about the stress relief. How are you doing? Okay, let me scream at the channel that we're live. Also, I have to do my stress relief breathing. So, the reason I picked this topic, by the way, guys, is that me? Yes, it's me. Okay, it's working. Is because some of you actually asked about when do you rest or sleep? Right after this, right after the live. This is so restful. Just kidding. After this, I will sleep. So, some of you asked about pulsars, and I don't know whether I sufficiently addressed the topic of pulsars in relation to neutron stars or not in the moment when it was asked a while ago. Now, we have talked about stellar remnants. There is a topic, probably a live episode called Stellar Remnants, quite literally, which covers all the different stellar remnants. Why I mention this is because neutron stars are a type of stellar remnant. Yay! So when stars die, they cease to have nuclear power that is making them burn and stay alive as stars. And pretty much when they run out of that nuclear process, they have to, they're the only thing remaining that is sort of a force in motion here would be gravitation. And stars are very massive objects, and they tend to collapse under their own gravitation if there is not an active nuclear reactor in their belly that's doing more and more nuclear reactions. So once the nuclear reactions start to kind of taper off, die off, the star reaches a point where pretty much the heavier elements from the lighter elements have been made, and it's kind of running out of the material to convert, or it's at the end of the processes pretty much that were dominating the making of those heavier elements. There's lots of different factors involved there, but at some point it's gonna kind of not do the nuclear power stuff anymore, and it will start to die. That's where it dies. Because see, if the sun was not burning, if the stars were not burning, our sun makes helium from hydrogen. If this process were to stop, then that's not good. That's basically, for our sun, actually, hopefully it'll do a few more things too when it gets older. But pretty much you want to be making some heavier element from some lighter element. That is the nuclear reaction. That is the nuclear power that keeps a star burning. For example, our sun is one example of a star that's burning. So once you are kind of done burning for various reasons, you basically, and one of the important reasons actually has to do with binding energy of the nucleus. So certain elements are more stable than others. For example, a lot of stars may have an iron core. Iron is a very stable nucleus, and that kind of goes into nuclear physics, and we can talk about that separately. But pretty much these are sort of the reasons why sometimes a star will kind of stop doing its nuclear reactions. It's kind of done, okay? And then it will collapse. This collapse part is a whole physics of its own in astrophysics, and it is called supernova. So when a star dies, there will be this massive explosion. Depending on the star, depending on the supernova, depending on what happens, there are actually some categories of supernovae as well. And that is the process of the death of the star. There are people researching that. There are people who simulate that. You know, it's a lot of different things going on with that process as well. So I'm kind of skipping over a lot of details. But then I'm trying to drive to what happens after that. So once a star dies and it finishes dying, it has done its supernova, and it's collapsing under its gravity, and blah, blah, blah. Time passes and it has collapsed down to a compact object. That compact object is a stellar remnant. So pretty much as gravitation wins and a star has completely died, basically what's left over is called a stellar remnant, literally stellar remnant, the leftover of a star, right? And this is generally a compact object. Why is it a compact object? Because a ton of mass has collapsed into something under its own gravitation. So a very extreme kind of collapse has happened, which has compressed that material that has collapsed to a much, much more compact object. So such a compact object is a stellar remnant. And there are three types of stellar remnants depending on the mass of the original star. Very interesting. In astronomy, you will find, in astrophysics and astronomy, you will find that oftentimes the most important driver of the physics and what happens is the mass of the object. So this is no different. Literally, depending on the mass of the star, the stellar remnant will either be a white dwarf, a neutron star, or a black hole. So those are the different stellar remnant options. And depending on the original mass of the star. So some stars are just destined to become a white dwarf. For example, our sun. Some stars are destined to become a neutron star. Neutron star has the name star in the word, but it's not a star. It's a dead star, okay? Some stars are destined to become black holes because of their original mass. So basically, all of that is to say that if you're a more massive star, your gravitational collapse will be more extreme, and you will make a more extreme compact object, okay? And so that compact object can either be the most extreme compact object, which is a black hole, or the still very extreme compact object, but less extreme than the black hole, which is the neutron star. And then the least extreme compact object, which is the white dwarf. But they are all pretty extreme in some sense or other, and they're all compact objects. A lot of material has compressed down to something very small in volume compared to the original star, especially, okay? So one of these stellar remnants, the three types, once again, white dwarf, neutron star, and black hole. One of these stellar remnants is the neutron star. And that is what we will talk about in some detail tonight, because this neutron star is what makes a pulsar. And some people on the channel actually have asked about the pulsar. Hello, Pranay. Was there leopard on Mars? Not that I know of. I don't believe that there has been any leopard on Mars or any alien on Mars. And somebody else said hi. Hello. So let me address really quickly about aliens. It really depends on your definition of an alien. If there is some sort of extraterrestrial life that is present on some other world, such as Mars or such as any other planet really, exoplanets or whatever, that would be in my book an alien, because an alien to me is just an extraterrestrial, as in not of this earth. So they don't have to be as magnificent as a leopard. They could be single cellular for all I care. They could be an organism made up of two cells on a different planet, and I would call that an alien. So aliens can be potentially a lot more boring or a lot less boring, depending on what is going on and what type of alien it is. Sprout Seedly says, hello, remember me, I'm Gladys. Hi, Gladys, how are you? So coming back to this, which is the neutron star, and thank you so much, and keep your questions coming. I will occasionally break, of course, to look at all your comments and say hi to everybody and read your questions, okay? So let us now go into the neutron star topic. I might have lost it, but it's actually right here. So why we picked neutron star to talk about tonight is because, again, it is related to pulsars, and we won't say everything there is to say, but we will touch upon this topic. And because somebody asked about pulsars, it lets me to talk about neutron stars. And also, I love the stellar remnants topic because it kind of allows me to talk about stars, their dying, the different, it kind of brings together a lot of things. And it also helps me to clarify that it can be a little confusing, the naming of all this. Neutron star is not a star. Neutron star is named neutron star, but it's actually a stellar remnant. It's a compact object. So let's go back a little bit in time now, because remember, we are in the intersection of particles, quantum, astronomy, astrophysics, all of that, right? When we consider something like the neutron star, another reason why I love it so much is because it also has to do with quantum mechanics, particle physics. Hello, Mr. Ayub, how are you doing? Oh, very nice. Your legs are good. Oh, good. So, when it comes to neutron star, perhaps we should spend a little time talking about the neutron at all. So, as you know, the neutron is a type of particle. And actually, it's a type of particle that wasn't discovered right away because it's neutral, right? So, it's kind of amazing how and in what order particles were discovered. And pretty much people thought maybe that the nucleus was just one thing, that actually, before that, remember how people thought that the most fundamental unit of matter was an atom. But then they discovered the nucleus, and then inside of the nucleus resides the neutron. But the neutron as a particle was not discovered right away. So who discovered it? James Chadwick. So James Chadwick discovered the neutron in 1932. So years after we had special theory of relativity and general theory of relativity is when we are discovering the neutron. So 1932 is quite deep into the 20th century of various amazing things have been discovered already and are being worked on actively. So I find it interesting how the neutron was not discovered before 1932. So 2 years after James Chadwick, who himself lived from 1891 to 1974, discovered the neutron in 1932, a German astronomer and a Swiss astrophysicist, Walter Baade, I don't know if I'm saying that right, Baade, and Fritz Zwicky, oh, I know Zwicky, of Mount Wilson Observatory proposed the existence of neutron stars. So first of all, they discovered the neutron. So that's cool. They discovered the neutron. Again, it was discovered later on because it's neutral. And, if it doesn't have a charge, then that would be difficult, right? To kind of see it if you're, say, using electromagnetic waves to see it. These two astronomers, so Walter and Fritz Zwicky, who also coined the term supernova, went on to suggest that supernovae represent the transitions from ordinary stars into neutron stars, which in their final stages consist of extremely closely packed neutrons. So why we're talking about the neutron is because a neutron star is a compressed, compact object which has extremely closely packed together neutrons that are being held in place by neutron degeneracy pressure. That is something that we will look at as well. So neutron degeneracy, this is something that plays into this because remember of the extreme conditions in which a neutron star or a stellar remnant is made. Because of the extreme gravitational collapse, things compress down to the point of this neutron degeneracy. So because neutron stars are formed when the degenerate core of an aging supergiant star. So first of all, you'd have to be a supergiant star. Our sun, is a star on the main sequence, and its mass is not big enough, for example, to be a neutron star. When it dies, most likely it will be a white dwarf. This type of neutron star, stellar remnant, would come from something like a supergiant star, a type of star, a bigger star. So once again, because neutron stars are formed when the degenerate core of an aging supergiant star nears the Chandrasekhar limit and collapses, we take the mass of it for a typical neutron star mass. So Chandrasekhar limit is something that we've kind of mentioned in the past, but it is an important mass in astronomy. A 1.4 solar mass neutron star. So that's the Chandrasekhar limit, is a 1.4 solar mass. So see how it's above our sun's mass? So that's sort of the limit. A 1.4 solar mass neutron star would consist of 1.4 solar mass over Mn, which is the mass of the neutron, which is around 10 to the 57 neutrons. In effect, a huge nucleus. So it's almost like all that material that compressed to make the stellar remnant which is the neutron star, it's almost like at that level of compression, these atoms are not distinguishable from each other. The nuclei of them are not distinguishable from each other. They're all very closely packed, so closely packed that they are in effect almost like a huge nucleus, you basically cannot tell apart, oh, this one is the nucleus of that one and then another nucleus. You can't really count, you can't really tell them apart, is how closely packed they are. You cannot pack them any closer. And there is a reason for that. They're held together by gravity. So gravity would have smooshed them even further, but they are held in place to where they cannot be compressed anymore because of neutron degeneracy pressure. Okay, so this comes from quantum mechanics. Because of quantum mechanics reasons, the gravitation has reached its limit of smooshing this material any further, and it is held or supported by the neutron degeneracy pressure, and it's pretty much like one big atom or one big neutron instead of the individual neutrons at that point. That's how it is. So let's see. Approximately 10 to the 57 of these neutrons are hanging out together, held together by gravity and supported by neutron degeneracy pressure. If you have the mass of the neutron star to be 1.4 solar mass, the radius of the neutron star is 4,400 meters. So they've done some math. Basically, because I'm not showing the math because it's just a formula that I would read out, but pretty much basically because we know that it's held together by gravity and supported by this neutron degeneracy pressure, you can actually solve for the radius of this neutron star, or at least get an approximation for the radius of this neutron star. So if you put that the mass of the neutron star is basically this Chandrasekhar limit of 1.4 solar masses, you would get this radius to be around 4,400 meters. So as we found, we haven't talked about this, but they actually found that this estimate is too small. And the actual radius of a 1.4 solar mass neutron star lies roughly between 10 and 15 kilometers. So they did some more corrections to that. And we basically say, it might not be exact, but we basically say that a neutron star's radius is around 10 to 15 kilometers, okay? So after doing the degeneracy pressure and the gravitation, all that math, pretty much, at first they got 4,400 meters, but then they corrected it to between 10 and 15 kilometers. So that's why we say that a neutron star radius is about the size of Manhattan or things like that. Things, comparisons like that you might come across. But all of that is to say that it's a very small radius compared to the original star's radius and the original star, how big it was, mass and everything. 10 to 15 kilometers is very tiny, so much smaller than the Earth, right? And the Earth is a planet, that too not a very big planet. Did you know that finally we saw the atom? Hi, Sukha. Hi, Pranay. How are you doing? Continue to say your comments. I appreciate it. So next we come to the density of the neutron star. Since the neutron star is so compressed, so compact, it's 10 to 15 kilometers. This really means that it has a very, very, very high density. So this incredibly compact stellar remnant would have an average density of 6.65 times 10 to the 17 kilograms per meter cubed. So 6.65 times 10 to the 17 kilograms per meter cubed. So greater than the typical density of an atomic nucleus, which is 2.3 times 10 to the 17 kilograms per meter cubed. In some sense, the neutrons in a neutron star must be touching one another at the density of a neutron star, because even the atomic nucleus, depending on which one, has various things in it, protons and neutrons, depending on which element. But a neutron star's density is bigger than the average atomic nucleus density. So definitely the neutrons in the neutron star is more touching each other, like in a very closely packed environment than usual. At the density of a neutron star, all of Earth's human inhabitants could be crowded into a cube 1.5 centimeters on each side. So if we were all packed into a cube of 1.5 centimeters on each side, then that's the level of packedness of this neutron star, of the typical neutron star. Oh yes, of course. Video ko hype karna mat bhulna. Of course, yes. Please share the video with me later on. So, the pull of gravity at the surface of a neutron star is fierce. For a 1.4 solar mass neutron star with a radius of 10 kilometers, G, as in the acceleration of gravitation for that neutron star, would be 1.86 times 10 to the 12 meters per second squared. 190 billion times stronger than the acceleration of gravity at Earth's surface. So this is the thing with compact objects or stellar remnants that collapse under gravity. Gravitation is very powerful, and that collapse will be very extreme, and the object will be very compact, meaning the G on it that we would feel would be very high. It's not our regular weight that we feel here on Earth. It would be 1.86 times 10 to the 12 meters per second squared. So, pretty extreme. That is a lot. An object dropped from a height of 1 meter would arrive at the star's surface with a speed of 1.93 times 10 to the 6 meters per second, which is about 4.3 million miles per hour. So if you wanted to go, sometimes I want to tell the Boston drivers this, if you want to go at 4.3 million miles per hour, making a big noise, why don't you move to a neutron star? And spare me the horror. So, some inspiration for aggressive drivers. Just saying. And you don't even have to drive, you just have to drop from a height. You know what I mean? Acceleration will be taken care of by the neutron star. Okay, so now that we looked at a bit of the neutron star definitions, let me decide if I want to talk about the equation of state or not. If anybody has any questions, comments, let me know in the chat. I will take a few sips of my tea and go on to the next section. It might be that I skip over the equation of state and go to, you know what? Yes, neutron star. So we will talk about neutron star models, because that's something I have never talked about. And then we will go to pulsars. Okay? How is everybody doing? Is there something on my mouth? Okay, so we will continue. So, because these objects that we speak of in astronomy are quite far, to understand them better, people work on models, simulations, basically computational ways to simulate these objects and to study them. Okay, so here we have some models, actually. So composition of a neutron star, there's a whole table of different types of neutron star models here that we can go over. But this table basically summarizes the composition of the neutron star material at various densities, because we talked about the density of the neutron star, right? We talked about how the density of the neutron star is quite high. But that doesn't mean that you cannot play with those numbers for the density of the neutron star and basically kind of see what the physics would be depending on its density. So at various densities, after an equation of state that relates the density and pressure has been obtained, a model of the star can be calculated by numerically integrating general relativistic versions of stellar structure equations collected at the beginning of another section. So we will skip that. The first quantitative model of a neutron star was calculated by J. Robert Oppenheimer. So you might have heard of this name. So Robert Oppenheimer is from 1904 to 1967, and G. M. Volkoff. So these two people at Berkeley gave us the first quantitative model of a neutron star. And we have an entire, let me see, 16.11. Oh, I see. We have a sort of a cartoon here of what they thought this neutron star looks like on the inside that I can show you as well. So this shows the result of a recent calculation of a 1. So they basically assumed for a 1.4 solar mass neutron star how everything should look like. So the details are kind of sensitive to the equation of state used, but there are some general features that we can talk about. So first of all, this looks like that there is some kind of core, there is some kind of interior, there is some kind of inner crust, and there is some kind of outer crust. Those are sort of the parts. And depending on which density or transition density, if you will either have a type of degeneracy pressure, and you will have a different kind of composition. So the composition and the degeneracy pressure will depend on exactly what density. So this is a bit of a detail. So if you are not into these details, you can skip this part, but pretty much I'll go over it real quick. So if your transition density is around 10 to the 9 in kilograms per meter cubed, then your composition is going to be iron nuclei and non-relativistic free electrons. So I'll go over a couple of these. And basically the degeneracy pressure would be same as an electron degeneracy pressure. If on the other hand, if you have something like a transition density or the density of 4 times 10 to the 14 kilograms per meter cubed, that's quite high, quite a bit higher, then you would have a neutron-rich, hi Neville, then you would have a neutron-rich nuclei, free neutrons, relativistic free electrons, and then still the degeneracy pressure would still be the electron degeneracy pressure. It's almost like, because we know that white dwarfs have electrons and held up by the electron degeneracy pressure, it's kind of like they're studying and making models of the neutron star, keeping the various parameters kind of flexible, okay? And then if you have something like a density of 4 times 10 to the 17 kilograms per meter cubed, then first of all, there would be some pion production, it seems, and then you would have superfluid free neutrons, superconducting free protons, relativistic free electrons, other elementary particles maybe, and you would definitely have the neutron degeneracy pressure. Okay, so this is all of this is to say that depending on, if you, in the models for the neutron star, if you play with the density, you might just get different types of physics that are supported by that density, okay? So again, the details are sensitive to the equation of state used, but there will be some typical features that we can still talk about. So what are these? The outer crust consists of heavy nuclei in the form of either a fluid ocean or a solid lattice, and relativistic degenerate electrons. So there is some, so this section will hopefully eliminate that there is still some diversity even within a neutron star. It's not just that every neutron star is the same and it's just a bunch of, there is some diversity within the composition. So we can talk about that. So once again, the outer crust consists of heavy nuclei in the form of either a fluid ocean or a solid lattice and relativistic degenerate electrons. Nearest the surface, the nuclei are probably just iron with Fe 56 and 26. You can get the best price for your home. What do you mean, Army? So iron 56 is pretty much nearest the surface, the nuclei are probably just iron 56. At greater depth and density, increasingly neutron-rich nuclei are encountered until neutron drip begins at the bottom of the outer crust. So there is the outer crust, and then there's the bottom of the outer crust, which is where we start to get this neutron drip. The inner crust consists of, so after the outer crust, inside is the inner crust, consists of a three-part mixture of a lattice of nuclei, such as, I think this is krypton, Kr-118, so a very heavy element. The mass number is 118, and the Kr, I think it's krypton, but please do check because I am not too familiar with that element. But anyway, they're thinking that the inner crust consists of a three-part mixture of a lattice of nuclei, such as krypton, superfluid of free neutrons, and relativistic degenerate electrons. So there are some superfluid free neutrons and relativistic degenerate electrons. Because again, in this extreme environment, the neutrons are acting like one. All of the neutrons are smooshed. All of the neutrons are acting like one big neutron. Okay, so they're acting like a superfluid. So, and then there's relativistic degenerate electrons as well. And keep in mind that white dwarf, which is the stellar remnant for the lower mass stars, are pretty much, that's all you have is the electron degeneracy pressure in the white dwarf. Like it's mainly the electrons that are existing in that degenerate state. The bottom of the inner crust, so outer, inner, next. The bottom of the inner crust occurs where the density is equal to the density of the nuclei. Interesting. And the nuclei dissolve. Okay, I see. Okay. The interior of the neutron, so I'm not entirely sure what that sentence meant, but we'll keep going. The interior of the neutron star consists primarily of superfluid. Oh, okay, I think they mean the interior of the neutron star. The superfluid neutrons might be what they're talking about. Okay. The interior of the neutron star consists primarily of superfluid neutrons with a smaller number of superfluid, superconducting protons, and relativistic degenerate electrons. There may or may not be a solid core consisting of pions or other subnuclear particles. The density at the center of a 1.4 solar mass neutron star is about 10 to the 18 kilograms per meter cubed. So we don't exactly know if there is a core or not. So it's sort of, at least at the time of this book. So this book is called, this is An Introduction to Modern Astrophysics, second edition by Carroll and Osley. Here's the book. And this book is from my college days, from a class in astrophysics. Hello, Gustavo. How are you doing? Hi, Army. I am in Boston, Massachusetts of the United States of America. Of course. How are you? I can't see the flag very well that you put in the comment. So you might have to tell me which country you're from, because it's a very tiny, tiny flag. Doing well. What about you? I'm good. We're just talking about neutron stars and pulsars tonight. I might get into the pulsars tomorrow night, but tonight we started off the topic. And because pulsars are basically neutron stars, I started the topic of Fiji. Oh, okay, perfect. Welcome to Fiji. Yay. I love that name, Fiji. The country name. There is Baji. This one is Baji Baba, the kitty cat of this channel, and his siblings. Good to meet everybody tonight. Please do like, share, and subscribe. Did you like and subscribe? So, Fiji is such a beautiful country from what I've heard. He looks so cute. Yeah, there he is. There he is. So, we are talking about neutron stars tonight, and we're going into some different details than we usually do, because I figured we will talk about this from this other book, because one second, I'm looking at my other screen, because we have actually talked about neutron stars in the past in a different context and from a different book as well. If you're new to the channel, then we have lots and lots of I missed your other streams. Hi B, how are you doing? We have lots and lots of content posted that I did live, as in lots of live streams like this, long ones. Under the live tab of my channel. So please do like, share, subscribe. Please do subscribe, and then you can see all these lives. And so we have actually covered the topic already in a different way. Did you watch that new Fantastic Four black hole scene? I did not. I still haven't seen that movie. How was it? Tell me now. Okay, so next we will talk about the Chandrasekhar limit for neutron stars. Chandrasekhar, of course, a very well-known and successful astronomer, astrophysicist, given us some important things like this. So let's see. Like white dwarfs, so white dwarfs especially, we know there is the star's mass. Any star that is basically below about 1.5 solar masses, when it dies, will become a white dwarf. Oh, I'm the guy who asked if it was okay if we didn't discover a unified theory of gravity. Oh, very nice. Oh, I love your questions. I did not see the movie, but thank you for coming back to the channel. Thank you for coming back to the live. How have you been? So, the stars' masses, the stars that are basically lower mass, like about 1.5 solar masses or less, when they die and collapse, they would become a white dwarf. So that's what this white dwarf reference means. I think you'll enjoy that scene. Oh, very nice. I haven't seen a movie in quite a while, actually. So I should check it out. So, like white dwarfs, neutron stars obey a mass-volume relation of basically mv equal to a constant. So neutron stars become smaller and more dense with increasing mass. So as the mass increases, the density, as the mass increases, the density increases and the volume becomes smaller and smaller. However, this mass-volume relation fails for more massive neutron stars because there is a point beyond which neutron degeneracy pressure can no longer support the star. So what do we mean by neutron degeneracy pressure supporting the star? It means that if neutron degeneracy pressure cannot support the object, I don't really want to say star because star would be a proper star. This is a dead star. If neutron degeneracy pressure or electron degeneracy pressure in the case of a white dwarf cannot support the star anymore, it will continue to collapse further. So it will continue to collapse further and further, and that is where it would become a black hole eventually, right? So there is a point beyond which neutron degeneracy pressure can no longer support the star. Hence, there is a maximum mass for neutron stars. So we know that a neutron star will have a maximum mass because neutron degeneracy pressure is the force at play for supporting this type of star or dead star. Otherwise, it would have kept collapsing further under its own gravitation. So we know that in theory, because at first when these things were theorized, people didn't know that black holes were real. Now we know. Now we do. Now we know that black holes are real. So definitely, if not for the upper limit on a neutron star, we would know that, well, the thing can keep on collapsing and go past the neutron degeneracy pressure limits and become a black hole. So there is a mass, which would be the maximum mass for a neutron star. After that, it would become a black hole. And that is why certain stars that are much bigger, when they collapse, they become a black hole because the neutron star that would be associated with that star is too massive to the point where the neutron degeneracy pressure can no longer hold the gravitation at bay, okay? If it has too much mass, then it becomes a black hole. So all of them explode first. Actually, don't want to say all of them because the explosions are kind of different for each one, but pretty much there will be some sort of explosion or supernova or nova with all of these types of stellar events and evolution. But if it has too much mass, then gravitation will be more extreme. That's right, yeah. So if the stars don't have too much mass, then they become either a white dwarf or a neutron star. So the lowest mass stars become white dwarfs. Those are held by electron degeneracy pressure. These are stars like our own sun, when the sun will die, that is. Then there are higher mass stars, sort of like giants, supergiants. When those die, they become neutron stars. That is held up by neutron degeneracy pressure against gravitation. Then there's the highest mass stars, the biggest stars. Those will all become black holes. Okay? So, yes, so that's, and one of these options we're talking about right now is the neutron star, so the middle one. We're talking about the middle child at this time. So, there is a maximum mass for neutron stars, analogous to the Chandrasekhar mass for white dwarfs. As might be expected, the value for this maximum mass is different for different choices of the equation of state. So there is some diversity in the equation of state for a neutron star, and so we can't always say exactly. However, detailed computer modeling of neutron stars, so they probably had to churn out a lot of these options, along with a very general argument involving the general theory of relativity, which I like, shows that the maximum mass possible for a neutron star cannot exceed about 2.2 solar masses. So the neutron star itself cannot be much more than 2.2 solar masses if it is static. And if it is 2.9 solar masses, it can be, if it is rotating rapidly. So neutron stars can either be static or it can be rotating rapidly. And so depending on if it's static or rotating, it can be either 2.2 solar masses or 2.9 solar masses. And remember, this is the mass of the neutron star, which is of course related to the mass of the original star. If the mass of this also puts a limit on the mass of the original star. Okay, so if the mass of the original star is much bigger, then you would no longer get a neutron star. So they're all related. Okay, so maximum, once again, mass possible for a neutron star is around 2.2 solar masses if it is static, and 2.9 solar masses if it is rotating rapidly. And by the way, the rotating rapidly part is what will get us to a pulsar later on. So that's what that is. If a neutron star is to remain dynamically stable and resist collapsing, it must be able to respond to a small disturbance in its structure by rapidly adjusting its pressure to compensate. However, there is a limit to how quickly such an adjustment can be made, because these changes are conveyed by sound waves that must move more slowly than the light. If a neutron star's mass exceeds 2.2 solar masses in the static case, or 2.9 solar masses in the rapidly rotating case, it cannot generate pressure quickly enough to avoid collapsing. So there is something with this adjustment that it needs to make if the neutron star, so basically how quickly the adjustment can be made also kind of makes it a regular neutron star or not. So the result is a black hole. If the neutron star, if something, so because everything is held together by that neutron degeneracy pressure, and there's a lot of detail to that equation of state and whatnot for the neutron star. So say something comes in and disturbs this, it can collapse down to a black hole. Okay, so that's part of this as well. So pretty much this number, they're getting it from the fact that, well, much more than 2.2 solar masses or 2.9 solar masses would mean that it can't be stable. And so anything will kind of disturb it down to collapsing further and becoming a black hole. So the bigger stars that have bigger stellar remnants will make black holes. Okay, so the 1.4 solar mass is the limit for a white dwarf. 2.2-ish solar masses or 2.9 solar masses is for the neutron star. Anything bigger would be black hole. And then can you imagine looking at a spinning neutron star in person? So yeah, when we do see a spinning neutron star, those appear like pulsars to us. So we see them in the sky, and they have a period associated with them. So a very rapidly spinning neutron star will have a period associated with it, and that is actually a pulsar. So we do see them in person, just they're very far away. Where are you getting the material to build this Dyson sphere? Oh, I see. Okay. So, we will now go on to the pulsars, actually. We can at least, oh yeah, we can definitely talk a bit about the pulsars. So, next we will dive into pulsars. I skipped over a few more things with the neutron stars: rapid rotation, conservation of angular momentum, freezing in magnetic field lines. Okay. Next, we will talk about pulsars. How is everybody doing? I heard somewhere about pulsar being used as the most accurate clocks. I feel like that sounds familiar. Please do like, share, subscribe. Hi, Red Eye. So definitely relativity is taken into account when you do these neutron star models. Somebody mentioned time dilation. That's a good point. So when you do the neutron star models, you absolutely have to take into account relativity, special and general, because absolutely, for sure, neutron star environment is going to be a relativistic environment. Okay? So, I mean, everything is a relativistic environment, but classically, if you're moving at sort of classical speeds and whatnot, and you don't have too much mass, then relativity is just a little bit of a correction to the Newtonian mechanics. But if you're near or in the environment of something more extreme, then relativity is always the way to go. Phone Einstein and ask about how it works whenever you're near a massive object, okay? So, Jocelyn Bell spent 2 years setting up a forest of 2048 radio dipole antennae. I think it's antennas. I think antennae is associated with an insect, whereas antennas is the plural in this case, but okay. Antennas over 4.5 acres of English countryside. She and her PhD thesis advisor, Anthony Hewish, were using this radio telescope tuned to a frequency of 81.5 megahertz. So just a couple of astronomers doing their thing is the story we're talking about, because the discovery of pulsars has a story. Okay, so Jocelyn Bell and Anthony Hewish doing some radio astronomy in their backyard in the English countryside. So what they found when they tuned the radio telescope to about 81.5 megahertz, they found they were trying to study the scintillation that is observed when the radio waves from distant sources known as quasars pass through the solar wind. So, by the way, this reminds me that we've talked about quasars recently as well. If you want, you should go back and look at the episode on quasars. But anyways, moving on. In July so these people were set up to study quasars, okay? In July 1967, Bell was puzzled to find a bit of scruff that reappeared, so scruff, literally, that reappeared every 400 feet or so on the rolls of her strip chart recorder. Oh, very nice. Careful measurements. So basically, they were trying to look for the quasars. Then they find that there is this bit of scruff that keeps appearing every 400 feet or so on the rolls of her strip chart recorder. Careful measurements showed that this 1/4 inch of ink reappeared every 23 hours and 56 minutes. Every 23 hours and 56 minutes, indicating that its source passed over her fixed array of antennas once every sidereal day. because that's a sidereal day. Bell concluded that the source was out among the stars rather than within the solar system. So it cannot be too close. It's out among the stars because it is passing over her fixed array of antennas. I don't know. I think so, yeah. It's passing over the fixed array of antennas every sidereal day. To better resolve the signal, she used a faster recorder and discovered that the scruff consisted of a series of regularly spaced radio pulses 1.337 seconds apart, which is the period, the pulse period P. Such a precise celestial clock was unheard of. So the scruff consists of a series of regularly spaced radio pulses 1.337 seconds apart. And if you do this a lot and you always find 1.337 seconds for the period, that is remarkable, because what could be happening which has celestial clock, yes, what could be happening which has a period of 1.337 seconds precisely? Every time the period is 1.337 seconds. What could it be? So it's a celestial clock, like somebody had suggested here, but what kind of thing is it that is such a celestial clock? Such a precise celestial clock was unheard of, and Bell and Hewish considered the possibility that these might be signals from an extraterrestrial civilization. So here you go, they thought they were aliens. People thought this must be a celestial clock that has to do with aliens, like extraterrestrial civilization. Maybe they literally thought that they discovered aliens with this. If this were true, she felt annoyed that the aliens had chosen such an inconvenient time to make contact. She recalled, I was now 2.5 years through a 3-year studentship, and here was some silly lot of green men, little green men, using my telescope and my frequency to signal to planet Earth. Because, they were set up with the radio telescope with their antennas pointing at the same spot, the same spot every night, because they were trying to do the quasars, and quasars are not close; they're far, far away. So, she's like, I'm almost done with my PhD here, and now you try to mess with me. So I think she was not very happy, because she's like, don't interrupt me and my quasar work, aliens, because I'm set up for quasars. So you know how focused PhDs are. I can relate. So I was now 2.5 years through its 3-year studentship, and here was some silly lot of little green men using my telescope and my frequency to signal to planet Earth. So she literally thought this is somebody signaling to us. When Bell found another bit of scruff coming from another part of the sky, her relief was palpable. She wrote, "It was highly unlikely that 2 lots of little green men could choose the same unusual frequency and unlikely technique to signal to the same inconspicuous planet Earth." So she was very relieved, because she didn't really want to find aliens. I think she was more interested in just astronomy. So she's like, there's more scruff from a completely different part of the sky. And how, that would be really unlikely that aliens are using such a technique that is so similar from different parts of the sky. So Hewish, Bell, and their colleagues announced the discovery of these mysterious pulsars. So literally they just called it, literally these aliens, or not aliens, now I'm calling them aliens. Literally these astronomers just called them pulsars because they were pulsing. Pulsars are named so because the period is so precise, and literally you get that signal with that period over and over and over, such a precise clock that they literally call it pulsar. Something is that is pulsing, literally a pulse with the period over and over, same one, right? Very precise. So they called it pulsars, and several more were quickly found by other radio observatories. So this is the first time that pulsars were discovered, but then they found several more, some stuff that has that exact precise period pulsing away, At the time this text was written, at the time of writing this book, more than 1,500 pulsars were known, and each is designated by a PSR prefix for pulsating source of radio, followed by its right ascension and declination. So they found a lot more, and basically they just started calling these PSRs, pulsating source of radio, and would always take note of the ascension and declination in the sky. For example, the source of Bell's scruff is PSR 1919 plus 21, identifying its position as ascension is 19 hours and 19 minutes and declination is 21 degrees. Oh, how nice. So it's basically PSR for pulsating source of radio. 1919 is the ascension. 19 hours and 19 minutes is the ascension. And declination is 21 degrees. Aw, I like that. It has a meaning. So if in astronomy you ever see a sequence of letters and numbers, usually has a meaning, which I like. So so B was asking, Lil, do you think any PhDs brushed actual alien signals under the rug because they were locked in and wanted that degree? Of course, I would not be surprised. But at this point, I think they might want to find aliens because exoplanets are such a hot topic. So at this point, exoplanets are very important of a topic at the have been for a while. So maybe now they want to find aliens, but I could definitely see people who are really locked in to what they want to do, and they might. Sometimes it's an annoyance, really, when you find something else. What we're seeing are jets from the spinning star's poles, not because something is crossing in between us and that. Yes, so we will. It's rotating. The neutron star is rotating. So we're literally seeing the period of its rotation. And yes, it has a very strong magnetic field. So if a thing with a very strong magnetic field is also rotating like crazy, you get this type of pulsar or pulsating source of light. And that's what we see, but with a very precise period, and that period is because the neutron star is rotating like crazy. Eversor said, hi Eversor, you're here. Hola, how are you? Okay, so when I say rotating like crazy, exactly. Yeah, you have to focus when you're doing a PhD. I mean, I would be kind of annoyed. Actually, we were annoyed. The experiment I worked on, we were trying to find neutrinos, and we kept finding cosmic rays. So this thing that we're just now talking about, where they look for something and they find something else, is quite incredibly common, annoyingly so. It's actually very, very much a thing. I measured some extragalactic high energy, ultra high energy cosmic rays myself. Once that I did not intend to. Happens all the time. I was looking for a needle in a haystack, yes. And yeah. So I actually discovered, if you will, measured, discovered, whatever, doesn't matter. Some new cosmic rays that are extragalactic, ultra high energy. They're in my thesis. Some of them, a lot of them were discovered by the collaboration, and then I personally discovered some. My own ones. And so so I was happy, I guess, that I got these cosmic rays, but like at the same time, I was looking for ultra high energy extragalactic neutrinos from astrophysical sources. I think the consolation was that I was expecting to see some cosmic rays because it was already known that we get cosmic rays as a byproduct of that experiment. The cosmic rays are really cool too. They're not like, boring cosmic rays. They're, cosmogenic or potentially even astrophysical or whatever. Ultra high energy. They're ultra high energy cosmic rays. So it's pretty exciting, but it's not the main thing that we look for or we looked for in that experiment. So yeah, it happens. It happens a lot. B says, that's awesome. I tell my daughter about you. Oh, thank you. Didn't realize you have a daughter. Oh, wow. Hi, Kenan, how are you? Hello, where are you from? I'm in the US. How are you and where are you from? Does she watch my channel? Okay, so all known pulsars share the following characteristics, which are crucial clues to their physical nature. Most pulsars have periods between, 1 second, let me look at the time. Okay. Most pulsars have periods between 0.25 seconds and 2 seconds. So when I said that they're rotating like crazy, what I mean is that they rotate very fast. So that number we were getting earlier by Jocelyn Bell and her advisor, like what she got pretty much, because, the grad student is the one who's doing all the work. They found 1.337 seconds, right? So that is well under 2 seconds. So what I mean is that the pulsar, this neutron star, is literally rotating with a period of 1.337 seconds. That's very fast, right? It's very fast. It's a 2.9 solar mass compact object that's rotating once every 1.337 seconds. And they found more pulsars, and they all have periods between 0.25 seconds and 2 seconds, which is pretty tiny. That's a very fast rotation. So with an average time between pulses of about 0.795 seconds, the pulsar with the longest known period is PSR 18410456, which has a P of 11.8 seconds. So the average time of pulses can be another number, okay? Tarzan 5AD is the fastest known pulsar, which has a period of 0.00139 seconds, so very short, very short. Pulsars have extremely well-defined pulse periods and would make exceptionally accurate clocks. Oh, this is what you were asking about. For example, the period of PSR 1937214 has been determined to be P equal to 0.001557806 44887275. Lots of precision there for this pulsar. A measurement that challenges the accuracy of the best atomic clocks. Such precise determinations are possible because of the enormous number of pulsar measurements that can be made given their very short periods. So yes, you were correct that they do make very good clocks. The periods of all pulsars increase very gradually as the pulses slow down, the rate of increase being given by the period derivative, dp dt. Typically, this derivative is around 10 to the minus 15. And the characteristics, so the change in, yes, we're live. What do you think? Of course, this is me in the flesh. So this dp dt, the derivative of the period, is around 10 to the minus 15, so quite small. And so typically this p dot, or change in the period with time, and the characteristic lifetime, the time it would take the pulses to cease if p dot were constant, is p over p dot, which is a few 10 to the 7 years. The value of p dot for PSR 1937214 is unusually small. Unusually small, goodness. This corresponds to a characteristic lifetime of p over p dot equal to about 470 million years. Wow. Just in case you were wondering. So these are some characteristics of pulsars that we have kind of wondered about. So that's what we discussed today. Audrey looks like she just got back from a nice date, but it went bad and now she's reading on straight. I mean, that's not a bad guess. B says when she's with me, she does. She's 7. Aw. Well, I hope that your 7-year-old daughter sees our stuff. We aren't even close to 20 likes. Yeah, I know. It's been very quiet tonight, which is fine. Did you like my live? Thank you. Thanks for being here. Doro, hi. Haven't seen you in forever. And no, this is just a bit of lip gloss that I threw on before the live. After a bad date, it needs to be quiet. I did not have a date tonight, other than with myself. Okay, so there are three obvious ways of obtaining rapid regular pulses in astronomy. Binary stars. If the orbital periods of a binary star system are to fall in the range of the observed pulsar periods, then extremely compact stars must be involved, either white dwarfs or neutron stars. So that's another way. This is a pulsar model, basically. People kind of wondering about what makes these pulsars. Neutron stars are so small that two of them could orbit each other with a period in agreement with those observed for pulsars. However, this possibility is ruled out by Einstein's general theory of relativity. As the two neutron stars rapidly move through space and time, gravitational waves are generated that carry energy away from the binary system. As the neutron stars slowly spiral close together, their orbital period decreases. So I was going to say that if you expect a binary star system to be doing something, well, the two things that are rotating about each other, that system will give off the gravitational waves, and actually their spiraling will get closer and closer together. So you should be able to actually see that. Given how precise pulsars are, you should be actually able to see that difference. This contradicts the observed increase in the periods of the pulsars, and so eliminates binary neutron stars as a source of radio pulses. So they considered it, but hello, Grimmy. Thank you for liking the live. Oh, shut up. Thank you for liking. Did Doro make you? And has he given you a raise yet? uh okay, so we considered binary star systems to be pulsars, but turns out that pulsars are so precise, we should be able to see the spiraling together, getting closer and closer if these things were pulsars, but they're not. So pulsating stars, they thought about that. They thought about pulsating stars. I'm reading quickly. Okay, they ruled out pulsating stars as well for various reasons. We won't get into it. It's fine. Rotating stars. You should. This is like a sleep ASMR live. So then lastly, they also considered rotating stars, but that was also ruled out. Lastly, the only thing that kind of survived the harsh ruling out of what could be pulsars is actually the neutron stars. So let's see. So only one alternative has emerged unscathed from this process of elimination, namely that pulsars are rapidly rotating neutron stars. So as we saw earlier, and you should go back to the beginning of the live if you want to see this spoken about, neutron stars can either be static or they can be rotating. Rotating neutron stars are the main candidate for pulsars, and they have survived the various sort of logic that needs to be satisfied here. This conclusion was strengthened by the discovery in 1968 of pulsars associated with the Vela and Crab supernovae remnants. Hi, Varun. Oh my gosh, Varun, there's Baji. How are you, Varun? And did you like the live? It's been so quiet tonight. Thank you for the hearts. Baji is sleeping. We can do a close-up of Baji too if needed. Thank you so much for liking the live and for coming to the live and seeing our shorts and videos. Thank you. 20 likes. 20. So when we saw the Vela and Crab supernovae remnants in 1968, today dozens of pulsars are known to be associated with supernova remnants. That's the other thing, is that we saw them in association with supernova remnants. And remember how neutron star is a stellar remnant. So supernova remnant, stellar remnant, neutron star, all of this kind of went together. And people were like, okay, yes. In addition, the Crab pulsar PSR 053121 has a very short pulse period of only 0.0333. 0.0333 seconds. I'd love a close-up. Anybody else popping a champagne bottle tonight? Oh, are you drinking champagne right now? What are you celebrating? Oh gosh. I am 1/4 rotating neutron star. Oh. Doro, Varun, let's not talk about politics. And I'm sorry about anybody's untimely you know. Untimely, very untimely. It's not even politics. Isn't everything politics that you time out, Dora? So I live under a rock. Actually, I live on a rock called Earth. 333 0. No, you got it. 0.0333. Yeah, but Varun is a good friend of this channel. Don't time him out. It's okay. It's okay. As in, it's okay. As in, Varun is okay. So, in addition, the crab pulsar has a very short pulse period of only 0.0333 seconds. No white dwarf could rotate 30 times per second without disintegrating. And the last doubts about the identity of pulsars were laid to rest. So basically, they yeah. Basically, Adam! Oh my gosh, Adam is here. Adam, my friend, how art thou? How are you? Oh my gosh, a supporter of science is here. Adam! Finally, finally, finally. Yes. So basically, they knew that pulsars were associated with this supernova remnant. But then we know that supernova remnants can be, you know, a white dwarf, a neutron star, a black hole. So they were basically wondering, is pulsars they were basically wondering, is pulsars associated with white dwarfs, or are they associated with neutron stars? And basically, because they're like, this thing is rotating too fast. This thing is rotating too fast. They're like, no, this has to be a neutron star. So no white dwarf could rotate 30 times per second without disintegrating. And the last doubts about the identity of pulsars were laid to rest until the discovery of the millisecond pulsars, p about 10 milliseconds or less, in 1982, the Crab pulsar held the title of the fastest known pulsar. The Vela and Crab pulsars not only produce radio bursts, but also pulse in other regions of the electromagnetic spectrum, ranging from radio to gamma rays, including visible flashes. As shown, we will see the picture if you want. There's a big thing here. These young pulsars and a few others also display glitches when their periods abruptly decrease by a tiny amount. These sudden spin-ups are separated by uneven intervals of several years. Good night, Grimmy. I am good, thank you. Hope you're well too. Thank you. Aren't pulsars the identifiers they use on the Voyager probe to give our cosmic address? So people are taking back their likes now. Look at that. Oh no. We will survive. So, do you mean that they are precise clocks? Or what do you mean? I'm not sure. I'm not sure about the cosmic address thing. So, anyways, glad people are here. The nearest pulsar yet detected is only about 90 parsecs away. So that's pretty close. PSR 06331746, nicknamed Geminga, was well known by a strong source of gamma rays for 17 years before its identity as a pulsar was established in 1992, with a period of 0.237 seconds jamming up pulses in both gamma and X-rays, but not at radio wavelengths, and may display glitches. In visible light, its absolute magnitude is fainter than plus 23. So there is some interesting facts here. So, hi Army. I guess you could determine your, yeah, maybe. Facts Don't Matter says, what is the stream about? It's about pulsars from astronomy. So we've been talking about neutron stars. If you go back, if you rewind the live, then we've been talking about neutron stars, which is a stellar remnant when stars die. And we've been talking about pulsars because pulsars are actually neutron stars. I'm looking at my cut. There's a cut on my nose. So even though it wasn't confirmed it wasn't known at first that pulsars are actually neutron stars and especially rotating neutron stars is the main candidate of pulsars that have survived being a pulsar, being considered a pulsar. There is Baji. Here's Baji Baba. Army says, how old are you? I see, that sounds boring. She's old. Can I see a cat again? There's the kitty cat. We only want cats. Oh, good to know. That makes sense. Cats are pretty awesome. Good to know, everybody. Any more comments? I'm pretty much done with the topic anyways. Actually, let me check the time. It is, okay. It is 1:40 in the morning. So, you know, we have been discussing the neutron stars and pulsars, and there's actually a lot more details about pulsars that we can talk about, but not tonight. Probably another night because I'm a little tired. Okay. Oh, okay. You'll unsubscribe from me? What did I do? Hi, Adam. You know, I don't have to immediately agree or disagree with political statements on a freaking live about astronomy. Making my job harder here. I don't think it was you. I don't expect that. I don't know what you're talking about. What is the name? Oh, this is Baji. Of course someone felt hurt. Of course. Someone was literally hurt. So of course some people will be hurt. Of course. That's why it's difficult. Dezuzzu. Wait, am I saying that right? Dezzu. Dezuzzu is saying white pearl looks good. Oh, thank you. This was a gift. I see, that sounds boring. Team that pearl top with pearl one-line necklace. I have some pearl necklaces, but they're not just one line. They have some kind of pendant, which, oh my gosh, did someone do a super chat? Oh my gosh. I don't have a, what do you call, just a simple one line. I don't like the little pendant, so that's why I don't wear them. They were all gifts. Can you bring him? Oh, will do. Give my best to Baji Suji. Thank you, Varun. Actually, I want a Kardashian. I don't know what that is. Are you talking about who timed you out? It was Dora, not me. But I think we should also, when we make some kind of political statements, we should be ready to also get a reaction. You know what I mean? Especially if something is something like this, the news story of the today, that's not really cool to be happy about someone's untimely, you know what I mean, regardless of your political stance. But at the same time, I don't really want to talk about that here while I'm trying to discuss neutron stars and pulsars, because like my brain is focused on this, and now, you know what I mean, I'm locked in, and now it's just, I can't do it. I can't. I'm limited. So, okay. It was not my intention. It was a joke. Well, I don't know. I don't know if people think that was funny, Varun. But yeah, I'm sure you didn't mean anything bad, because why would you? Of course not. Of course not. So, okay, Grimmy says, oh, you're still here. Oh my gosh, after all the drama. I'm mad at all of you because you've caused drama in my life. People storming off, people taking their likes back, and me trying to teach pulsars is a great combination that can be found on this live stream. Thank you so much. I will clip that and record this forever. And I haven't even thanked Adam. Oh my gosh, Adam Dolson, thank you so much from Canada. See, the Canadian is helping us. We can't be peaceful in this country. So Canadians are to the rescue. Thank you so much, Adam. I not forgot, but I didn't have a chance to thank you yet. Thank you so much, Adam. Thank you for doing the super chat. Really helps the channel and helps to encourage me. Thank you so much. Grimmy is saying some explosive thing, probably. There, Vern says condolences. Thank you. Thank you. We should. Of course. We don't want to be insensitive. Good job. Good job, everybody. We love to watch a live. Here is Baji. A pretty good rule of thumb is that if you can't say anything nice, don't say anything at all and just release the files instead. Release the files? What files? Close your eyes. Close your eyes? Are we going to bed? I hope you get Grimmy. This is the thing about you guys, Grimmy and whoever else. Okay. Good. Hide that. Make a wish. Are you India? I am India. Can we just talk about the cosmos? Absolutely. She's literally ignoring aliens for neutrinos. Skeletor says if Canada ever takes over the world, we'll all be sorry. Don't you dare. Don't you dare now say anything political against Canada. Canada is the only one who's done a super chat tonight. US, you've been useless. US, useless. Doro, don't hide Varun Malik. Please, let him be. He's already said sorry for his earlier comment that he did not intend to be taken so seriously. If Canada ever takes over the world, no. I'm not reading that again. Are you believe in Jesus? Do I believe in Jesus? Sure. Sure, why not? While we're at it, why not talk about Jesus too? Let's talk about Jesus, politics, the news story. Can someone like the live, please? Thank you so much. And Adam, thank you so much. Thank you, indeed. Good night, Doro. Good night. I do think you should probably fall asleep now. Whenever I get here, it starts devolving into randomness. I mean, I was kind of wrapping up and then people joined, so I wanted to say hi. But entropy. Hi, Suk. Oh God. Yes. Hi, Sukha. Hi, Annie. Annie Frank. Hello, Annie Frank. Hello, Skeletor. I'm not saying it because I've seen this username before. So, okay. Next time, we will continue. So, I have, by the way, the book that we have been reading today is called An Introduction to Modern Astrophysics by Carolyn Osley. This is the Introduction to Modern Astrophysics, second edition by Carol and Osley. And we talked about neutron stars and pulsars tonight. If you joined late, then you might have missed the neutron stars and pulsars. Things were actually quite peaceful. And I got through a lot of the topic tonight. But then old people joined and I was saying hi and it did become more random. So sorry about that. But I was kind of wrapping up anyways because it's kind of late. Thank you, Adam, for the super chat. And thank you, everybody, for being here. And thanks for the likes and everything like that and supporting. Thank you. Grimmy told me... Oh, Annie Frank is here with Grimmy. Okay. You guys do take this live very seriously, I must say. It's only randomness when you're observing it. When you're not observing it, it behaves like a wave. Very true. Anyways, Adam, are you going to be here tomorrow? And I have a few topics in mind, but is there a topic that you want me to cover tomorrow night? I think I'll do a live tomorrow night as well. What do you think, Adam? Will you be here? So I just did the neutron stars and pulsars. I was thinking, let me see, maybe something with galaxies, a bit of cosmology. Chickpea break. Can you sing? I do sing sometimes, yes. Chickpea break. It's been forever. How are you? Wait, is chickpea break Dora, or is that you, chickpea? Or is that Dora? I can't remember. Adam says, I think I could. Yeah. Thank you if you're coming tomorrow night. What do you like more, astronomy, astrophysics, or cosmology? Bye, Army. Yeah, it would be good to set an alarm for an hour earlier. How about that? Chickpea break. Oh. Did you say something? Oh, chickpea break is saying Dora was water break. Chickpea break, how are you? How is Bahamas? Aren't you from the Bahamas? Dora was water break. I'm giving Dora a break from being a moderator. How about that? How about that? I can set a reminder around the same time. Yes, please set a reminder for an hour earlier. Gray holes. I can't see the difference between the three, like, give me three more specific options and I can choose better. I can't see the difference. Oh, so astronomy is study of the heavenly bodies and sources and objects and events. Astrophysics is more to do with the physicsy part of those things, like the physics of supernova versus observing a supernova, and the physics of the mechanisms of supernova versus, you know, that's astrophysics. And cosmology is the study of the universe. Grimmy says, okay. Why are you here then, Grimmy? Maybe you should also follow him. Ubaz says hi. Hi, Ubaz. There's some war going on in the comments. Go ahead. Go ahead and share the like. Share the like. Share the live. Like, share, and subscribe. Actually, hate comments are still engagement, so I don't mind. Go for it. Go for it. Ubaz says hi. Hi, Ubaz. How are you doing? I can't see the difference between the three. Okay, so I was talking about you do know that I can remove you, right? Grimmy. In fact, where's the block button? You know, it's been a hot minute since I've done my own moderation. Chickpea break. Hello. It's been a hot second since I've done my own moderation. But I do suppose that I have to take things into my own hands and remove the people who are creating too much drama here. Too much drama. How do I block somebody? I've never had to block somebody. Let me do that. Let me do that. Some people like to what do you call? Excuse themselves so very easily when it comes to doing something inappropriate, but don't want to tolerate the slightest comments from others, do they? It's called intolerance. Okay. Oh, I figured it out. I figured it out. Yes. I figured out how to block Grimmy. Bye, Grimmy. Thank you for nothing. Good night. Adam says stir the pot. Thank you, B. I do need new mods. Some of my mods, I mean, they barely appear anymore. And when they do come, they create drama and toxicity more than anything. So I'm glad we're having this conversation. And I can upgrade the situation while we're at it. Planet 9 Hunt. Boots Foot is freaky and interesting too. Or maybe the physics of neutrinos. Are you talking about a show? I'm not a very aware of show kind of person. I don't really know what that is. I can help mod too. Thank you. Let me make you a mod. B has been asking lots of good questions that are related to the topics. And so here you go. Thank you, B. Basically, the moderation is really just for people who spam a lot. Like, I'm pretty tolerant when it comes to whatever people are saying, because I'm guessing like this is it's an open platform. People come with their various opinions. They can say things. They can even hate on me. It's fine. But if they spam a lot, like what Grimmy was doing right now, like he's just putting one letter in every message. Obviously, it's an inappropriate thing to say, racist thing to say. So suddenly, they were so offended by what Varun said, but then these people suddenly, it's okay to be racist. And it's not even the first time that they've done that. So, such is the politics of this nation. Very racist sometimes. Same people who complain about other things. But anyway, point of it is that basically the point of moderation, he must have blocked me. I can't see him. No, I blocked him. I just blocked Grimmy from the channel. So hopefully we'll never see him again. But yeah, these people have been coming to my lives for the longest time, but they're not really very supportive, if you notice. Like, they just like the power of being a mod. They get other people to come to the live for their own entertainment. They don't care about the content. They don't care about me. I mean, not that they have to care about me, but like, they don't care about what's going on, but they want their friends to come, and it's like a little bros club for them here on the live where we're talking about physics and astronomy and cosmology. And I never usually, get derailed and talk about this, but I think tonight's the night. Tonight's the night. We'll talk about it, which is that for the longest time, some of these people who've been coming, yes, they come for attention. They don't really like the content. They don't really care about the content. They never support. They never do a super chat. They only use their power to basically bully me and others, etc. And the point of the moderation, whoever has kindly either served as a moderator or is now serving as a moderator, what I want is, if someone's spamming so much where I can't see the real comments of other people, and if I can't even see the comments and questions of others who are actually involved in the live, then I really want that person to be timed out, because we don't want to keep seeing their spam messages, right? But if someone says a comment which is in the gray area, I really don't care. It's okay, Like, I'm not saying that their comment is okay, but I'm saying if people want to discuss their comment, feel free. There's no need to throw a tantrum in the live, blocking people and hiding people to use your power as a mod. So I think someone who is more emotionally regulated would be a better choice to become a mod or to do one of these lives. So thank you so much, B. Thank you so much, everybody. I'll evaluate based on disruption. Yes, of course. So, I mean, I'm happy to get any help, really. Even the people who have moderated in questionable manners, I'm still very thankful that they helped me because I'm a small channel. Any help is welcome. But sometimes the help can be more harm than it is help because it's sort of a power dynamic, a power play, not as much to just kind of moderate. Moderate just means do everything in moderation. If people want to ask a lot of good questions, then go for it. But if you're spamming a lot, then you're hiding other people's comments. And that's not really fair. It's a platform for open discussion. In other words, okay? Everybody should feel included and feel like they can voice their things without, too much what's the word? Too much censor. That's the word. I'll evaluate based on disruption. Thank you. It's okay. They'll be gone once the heat death of the universe comes around. I guess the stream will be over too. Can you capture neutrinos? So yes. So depends on the... So, okay, let me talk about neutrinos really quickly because I was talking about that earlier and we kind of wrapped up the neutron stars and pulsars for now. So we can actually detect neutrinos. So when you say capture, basically, let me just say that so far, the way, broadly speaking, the way we detect neutrinos, so we don't really capture them, but we capture their signature. So what do we really detect? We detect some kind of signature from neutrinos interacting in some kind of material. So we don't really capture neutrinos and put them in a bottle or anything like that, but neutrinos, when they interact in some kind of medium, sometimes we call this a detection medium, that interaction will often have a signal associated with it or a signature associated with it, and that signature is what we usually go after in these various experiments, depending on which experiment and depending on the energy regime of the particle. So at one point I showed this, so I can show this again at some point, but basically particle physics experiments and particle astrophysics experiments are in various different energy regimes. Okay, so there are some that are low energy, there are some that are high energy, some that are more high energy, and then very high energy and ultra high energy. So yes. So exotic neutrinos are basically the ultra high energy and high energy neutrinos. Generally speaking, these are extragalactic in nature. They're not from our own galaxy, and they're from processes and astrophysical sources that are not in our galaxy, and they're coming from far, far away, hopefully, possibly from something very interesting, some transient event or some other thing in the sky that has happened, and a way to probe that thing is that neutrino that came to us. Yeah, so then this neutrino, right, the very high energy neutrino, the way it interacts, its signatures is going to be kind of different from, say, the neutrinos that are coming from our own sun. Energy regime, so therefore, is the biggest thing here. Okay, so pretty much any neutrino experiment is going to be set up so that we can basically see the signatures via some detection material. This could be water, the detection material, that is. The detection material could be water, it could be ice. In my experiment, it was ice. It can even be something like salt, actually. So you want these neutrinos to come in and interact in the detection medium and cause some kind of signal. The signal can be in different wavelengths of light, by the way. Sometimes the signal is a radio signal, and so then we need a radio experiment to see that signal. Sometimes the signal is an optical signal, and we would need PMTs to see that signal. So depending on which interaction and which energy regime you're in, you would set up your experiment accordingly. That gave me goosebumps. Energy regime is a new term for me. Energy regime. So yes, so I have actually a visual of this in one of my, it's in my thesis and also in some of the talks that I have, a lot of the talk, every talk I've given probably on the topic. So I'll show you that visual at some point soon here. We'll come back to that. But basically, the solar neutrinos are generally around in the MEV regime, energy regime, whereas there are things that can cause GeV, giga electron volt is a higher bracket of energy. Then there is, you could have 10 to the 15 EV, which is PeV. You could have exa electron volt, which is 10 to the 18 EV. So my experiment was exa EeV and above. So a big thing, pretty much whenever you go to study these neutrinos and figure out how to study them or how to detect them and what exactly you will probe, all of it goes hand in hand, and it all points back to the energy regime. So yes, it's very important. Energy regime, and pretty much you want to, all these experiments are kind of like cousins of each other. So you want to know like all of them and put them all in the same slide to kind of see where everything is. So that's what I have. How do these neutrinos get released from stars? So that's a great point. So actually, did you know that in certain processes, I believe, I have to cross-check, and we'll talk about the supernova stuff too next time. But sometimes a star can lose most of its energy in neutrinos. The neutrinos leaving the star is actually the star losing energy, and it's gonna, collapse under its own gravitation. So neutrinos, because they are weakly interacting, most things are transparent to them. They'll go right through it. So this is another reason why the detection medium is so important, because neutrinos can just pass right through things. What is to say that it will actually interact with that medium? So you want to set up your experiment such that there are many, many occasions of the neutrino interacting, or there are many, many chances for the neutrino to interact, because typically they don't interact, and they don't interact with electromagnetic force or anything electromagnetic, and they only interact with the weak force. So pretty much the longer you look, or the more detection volume that you look at, the better, because you're trying to increase the chance of actually some kind of interaction happening, because most of the time they don't interact with anything. So how do they leave the stars? They just depending on which process, lots of neutrinos are released in a supernova when the star is dying. But basically, in every nuclear reaction that, I can think of, pretty much all those nuclear processes in a star or whatever, generally speaking, will have neutrinos coming out as a byproduct. But if you lose a lot of neutrinos, then you have lost a lot of energy as well, and that is one of the key steps actually in supernovae. So we can, when we discuss that again, we will touch upon that, so that I can bring this back to you. But basically, neutrinos escape stars very easily because they are not colliding with things on the way out, right? Other things, photons, electrons, positrons, neutrons, protons, these things all interact with each other. So the more types of interactions a particle will have, say it interacts electromagnetically, it interacts with the weak force, all of that stuff. It has a substantial mass, right? Because neutrinos are also very low mass. They're not massless, but they're very low mass. But most importantly, they're weakly interacting. So it's the particle physics interactions of neutrinos are very limited. And so they're not meeting and interacting with other things on the way and getting trapped in the environment. In other words, they stay in the environment that they're in. Yes, they are a byproduct. I like to call neutrinos sort of the electron of nuclear reactions. You know how every chemical reaction has the electron involved? Neutrinos are basically in the same family of particles as electrons. They're also leptons, but they don't have a charge. Like electrons have a charge. That's why they participate in chemical reactions. Neutrinos don't have a charge, but particularly speaking, they are in the same family as electrons. They're much lighter though, and they don't have charge. And pretty much in nuclear reactions, they are always a byproduct, pretty much. But that's also not the entire story. The story is that they could stay inside the star, but they leave because the star, even as extreme of an environment as a star, is kind of transparent. Like even the sun, neutrinos will pass right through and then come to us, because if there is, say, a nuclear reaction somewhat in the depths of a star makes a neutrino, right? That neutrino could just stay in the star, right? Like, do you see my my thought process here? So say lots of things are happening in a star. A neutrino is born sort of in the depths of the star. Doesn't mean that the neutrino will leave the star, because it's sort of in the depths of the star. It could stay. If it was something else, like say electron or photon, it will interact. Like after being born as the side product of a nuclear reaction, it can interact. Other things like the electron or the photon will keep on interacting. So it keeps meeting other things along the way, and it's trapped in the star. Neutrinos are not doing that. To most other particles, they're very introverted. So they're like, I see you, but I don't care. I don't give a shoot. I see you, photon, I see you, electron, I see you, positron, and I keep moving. So the neutrinos just keep on moving, like me, actually. I'm very weakly interacting as well. So neutrinos just keep on moving. So they actually leave the star because they're not trapped inside the star. I mean, not all of them are leaving, but many leave. So, hi, cute world. So, and remember, supernova processes are also different than when the star is still starring, right? So we will come back to this. Tomorrow we will talk about the supernova. But there is a point at which during supernovae, certain things have happened, and those processes probably made neutrinos, right? And the neutrinos, instead of staying in the star, because they could still stay and be trapped and keep on interacting with the other things, but they don't, because they're neutrinos. They see the star as, oh, this is transparent to me. I will just move right through and leave the star. And with that, they actually leave with a lot of energy. And if I'm not mistaken, if I remember correctly, some stars lose most of their energy in neutrinos leaving versus, for example, the heat and light and whatnot that comes out of the supernova. So it's very interesting. So the main thing is that neutrinos are weakly interacting, and so that's why they can easily pass through things. Oh, and also, by the way, something I did not mention in all of this is the energy. Once again, energy regime is the key word, because I've been saying that neutrinos pass through things, but that comes with a caveat. Energy of neutrino matters. A higher energy neutrino will have a higher cross-section of interaction. So a lot of the, say, MeV scale neutrinos can pass through things just fine. Like the solar neutrinos, they're passing through us all the time, all the time. But if you have a higher energy neutrino, like GeV, PeV, whatever, even higher energy, then those neutrinos have more probability of interacting with material. Okay, so that's another thing to keep in mind as well. So yes, neutrinos think most things are transparent and they will pass right through as compared to other particles. But there's a caveat with energy. It's still very low. The probability of neutrino interacting with something is still very low, but the probability does increase with energy. And there's a whole paper on this by my advisor, Dr. Amy Connolly. Okay, so if you look up cross-section, high energy neutrino interactions, something like that, basically the relationship between cross-section of interaction and neutrino energy, then she has a paper on it. So you said something about the weak force. No, not quite. So the question you asked, yes, so B's question, oh, was that B or Adam? Adam's question I'll come back to. B's question, is there a mirror version? Yes, neutrinos have anti-particles, if that's what you mean. So there's a couple different particle, partner particles that we've spoken about, right? The common one is an antiparticle. So indeed, neutrinos have antiparticles. Neutrinos have antineutrinos. So all the time, these nuclear reactions, the Feynman diagrams, etc., you will see neutrinos and antineutrinos. So definitely, so the three types of neutrinos each have an antineutrino. So for sure. Now, if you're asking about the super partner particles, neutrino, that one I believe is not discovered yet because I don't think that supersymmetry is confirmed yet. Once it is, please do inform me because I live under a rock. But pretty much there could be a couple different partners, either an antiparticle partner, that would be the antineutrino. Yes, neutrinos do have antiparticle partners. And the supersymmetry particle would be the sneutrino, which I'm not sure that there is evidence of yet. Hello, madam. Where are you from? Hi, Shri. How are you doing? I'm in the US. I wonder if there's an anti-Majorana particle. Okay, now let me come back to Adam's question. So Adam asked, so are they bound in the core by the weak force? No. So they're not bound by the weak force. There's not like a bunch waiting in the heart per se. It's more the case that a supernova is an explosion, right? So it's like an extreme environment. It's a transient extreme environment or a transient extreme event in the sky. Because the star was chilling. I mean, a star is a pretty extreme environment too. The star was chilling, but supernova in comparison to star is even more, of course, it's an explosion, more extreme and transient, right? So the supernova environment can trigger more nuclear reactions for the time of the supernova, when the supernova is happening, and then it all stops, right? And it just collapses back down to the compressed object or the stellar remnant. But basically, in those supernova related processes too, neutrinos can be made, and those neutrinos, things are getting ejected out anyway in the supernova. There are layers of material, and if some of those, say, processes are happening in those layers of material, things are getting accelerated, more processes are happening, neutrinos are getting made. Those neutrinos will get the F out of the star. They're not necessarily trapped in the core. It's just that we're making them, and instead of staying in the star or staying in the environment, they leave completely because they can, because they don't interact much as compared to the photons, electrons, hadrons, protons, neutrons, photons, electrons. Those things will interact way more than neutrinos will. So that's why neutrinos are the first to leave, pretty much. Even photons, right? Light, getting light out of something seems trivial, but it's not. A lot of photons are busy getting trapped or interacting with other things in that environment. So photons don't have to come out right away. Neutrinos might come out easier. In fact, they do come out easier, okay? So it's like, yeah, I mean, and that's why neutrino is considered a strong astrophysical messenger. I mean, ultimately, what is light? It's an astrophysical messenger. It's something that tells us about a process or a source or an object. But for light, for the light to enter our eyeballs or our telescopes means that photons left that source to come into our telescope and our eyeballs, right? What if these photons were busy interacting still in the source? Then we wouldn't have those photons entering our eyeballs. So the same thing, like if we had neutrino eyeballs, we might see more of them sometimes. Stuff like that. So it's very interesting. Basically, we want to have more than one way of seeing astronomy, things happen. And that's why we do multi-messenger astronomy now, because photons give us a picture, neutrinos can give us a picture, cosmic rays can give us a picture, and so on and so forth. Gravitational waves can give us a picture. And so this is why in the modern age, as in of the current times, we always look at things in multiple ways, because one thing will only give you part of the picture. That makes sense. I guess there would be a lot more nuclear reactions going on as it's getting ready to blow. They're like, I'm getting out of here, partner. Yes, as the star is blowing up too. So literally what I mean is during the explosion, as things are actively supernovaing. So basically there's the star physics, right? But then there's also supernova physics. The physics of the supernova is its own thing. There are people who study just the supernova, right? So there's a lot happening in the supernova. So in that environment, in the supernova environment, neutrinos can be made, but also neutrinos are made in the regular star as well. So, all kinds of neutrinos can be coming out at various stages. How the definition of atom and particle by science are highly true. Oh, that's a great question. How the definition of atom and particle by saints are highly true as same as scientists. Their definitions are far advanced. How did the saints have an intuition for atoms? So I don't know. Sometimes science is done. So it very well could be that ancient times people did do science and people did know things, but they were not documented in the same way that we understand now, or documents were not kept. And so some of it got lost, and actually this was known before. So I would imagine it's something like that, like where modern is not always so modern, right? Sometimes something we understand now, it was understood way better in the past. It could be like that. How common would you say these MeV neutrinos from our own sun are? Like one swimming in a neutrino soup right now? So we should look it up. I don't have the exact number, but it's a lot. So that's a great point. That's a great way to ask the question. I'm glad you said it that way. You said, how common would you say these MEV neutrinos from our sun are? Great point. Thank you for saying MEV neutrinos because the energy matters a lot. So the sun, I believe, does produce a lot of MEV scale neutrinos. And I believe that, I think it's something like, I don't want to say it because I don't want to say it wrong, but like it's something like just our thumb, there's like many going through our thumb right now, or you should look it up. It's some very high number. So in the current environment of our Earth, of course, the biggest source of neutrinos is the sun, is our sun. So yeah, it's a lot. You should look it up and let me know. Look it up and tell me how many neutrinos from the sun are hitting just our thumb at any given point, like say per second. I think it's a very high number. Because think about it. Think about it. Like when the sun, like, I mean, right now it's night here, but you know how bright the sun is in light, right? Light is a particle that's emitted from the sun. Neutrino is also a particle that is emitted from the sun. So, you know, day and night is determined by the sun, and neutrinos are always coming, as in they're also emitted by the sun. They did science, but they called it something else. Yeah, I think they did science, but they called it something else, or they documented it different, and they might have done things different. But you Indian? Yes. I'm not Indian. No, Andre B. How far could MEV neutrinos travel through space? How far could MEV neutrinos travel through space? That's a great question. So, an MEV neutrino would travel through space forever until it decides to interact with something. So if it doesn't interact with another particle, and remember neutrinos only interact via the weak force, so probability of it interacting is quite low, it would just keep on going forever. Nothing stopping it. So this is actually why yes, that's exactly. The neutrino sun never sets because the neutrino sun, the neutrinos from the sun can basically go through the earth just fine. Yeah, look that up and see what it says. The neutrino sun never sets because those MEV neutrinos, I do believe, can go through the earth, no probs, no problem. So pretty much, this is another reason why we use neutrinos for multi-messenger astronomy, is because they point straight back to their source, because we don't expect them to interact on the way. So how far can it go? As far as it possibly can without an interaction. And it may be a while before it interacts because they interact so weakly. They don't interact much, right? This question, when you ask for other particles, is way lesser of a distance, right? There is, most particles will interact with something, another particle, along the way. Depending on the particle, that distance will be different. But for neutrinos, it can be long. EEV neutrinos, So part of it is the momentum, but part of it is, a lot of it is the fact that it's weakly interacting. EEV, hi Raphael. Hi Switzerland, how are you? I've been all right. How have you been? My dear lovely friend, what up? Long time no see. How have you been? Are you from Switzerland? Raphael, how are you doing? Did you guys all subscribe? You guys are all subscribed, right? Because some people unsubscribed from me tonight because of Varun and Doro and others. I don't want to just blame Varun. Varun, if you're still here, you better say something in the chat. Make up for it. Thank you, Jorge. Oh, that's right. Happy birthday, Raphael. Okay, so B's question, and that'll be the last question for tonight because I do have to go to bed. Hi, my dear lovely friend. Raphael. Oh, B saying yes to my, are you subscribed? Yes. Please do subscribe. The people who do like the physics content and the kitty cats, please do subscribe because apparently I'm losing subscribers now over politics and news. And I was absolutely not mentally ready to discuss either of those tonight. And so it's really sad that whatever. I guess it's okay if the people who, don't care about this content leave. It's fine. Happy birthday, Raphael. Thank you. Thank you to Switzerland. It's good to see you here tonight, Raphael. Usually I catch you when I go live earlier. But it's good to see you. Yeah. Happy birthday, of course. Of course. Okay, so let me just quickly talk about the EEV neutrinos. So no, it's not the fact that their EEV is why they can make it up to here. They make it up to here mainly because they are neutrinos. They interact very weakly. So do you see what I'm saying? If they had been obstructed by something, then they would not make it here. If they had interacted with something on the way, then they would make it here. So when we do see an EEV neutrino, because I do believe that we haven't yet, we have seen PEV neutrinos, okay? Then the exciting thing is that they do actually, these are the original neutrinos from that source because they wouldn't have interacted with anything along the way. And the first time that they interacted is in that experiment. How cool is that? So they're not sort of impurified by something that happened along the way because they're not charged. They don't get deflected by magnetic fields. They don't interact with other particles most of the time. So this is the original OG neutrino from that source, which is very exciting because if you catch if you detect a neutrino and it's a PEV neutrino from an astrophysical source, it's pointing straight back to that astrophysical source. So it's considered very special and, or at least to me, I think to the neutrino physicists, it's very special and reliable messenger of astrophysics. And most of the time nowadays, we want to use multiple ways of studying the source, okay? Like neutrino one way, light another way, gravitational waves another way, that type of thing. But EEV, like basically the momentum does have a role, but the most important thing is the nature of the neutrino is why it can make it to here, okay? We would see MEV neutrinos from far, far away too, I believe. But those ones might not be, okay, let me just say this, but please do cross-check this. MEV neutrinos from far, far away, unfortunately, might be very difficult because we have so many MEV neutrinos from the sun, right? So let's say you're trying to detect an MEV neutrino. Well, everything here is an MEV neutrino. Like there's so many from the sun that I think it could be pretty difficult to figure out which one is which. The large majority would be from the sun. So, and I'm also not sure that they would be very interesting. I think people generally, the higher energy neutrinos are of more interest, okay? Because those are made in processes that are more interesting, usually. But I could be wrong, so just double check that. Because the big thing about, whenever you're trying to detect a neutrino, you have to be very careful of the noise. Basically, whatever your signature is, whatever you're calling a neutrino, better stand out from its noise. If your noise is also MEV neutrinos, then that could be a tough life. You're the best in the world. Do not forget my bro. Oh, thank you, bro. Thank you, brother from another mother in Switzerland. Oh, you're talking to B, not me, B. I thought you're talking to me, like Ondri B, I see. I'm going to Canada, Toronto soon in October. Oh, really? Well, welcome to this hemisphere. Or not this hemisphere, because you're already in this hemisphere. Welcome to this continent. I think so. I think you could detect it, but it could be difficult to distinguish. Yeah, but I am not an MEV neutrino specialist. I worked on higher energy neutrinos. So the problems that are faced by different scientists are quite different. So it's my educated guess that it would be difficult to distinguish an MEV neutrino from other MEV neutrinos that are constantly bombarding from the sun. I'm guessing you could detect it. Yes, whatever number you found is the number. It's a very high number that goes through every centimeter every second. Yeah. Sounds about right. And it makes me wonder if they're not interacting or what's determining their movement. So they just move freely in space, Adam. They're a free particle. They just, whatever momentum they got initially, they just carry it throughout. Nothing is slowing them down. So their low mass and high momentum is part of it. So that's why I said that momentum is part of it. The energy is the EEV versus MEV is, Baji is right here. Yeah. He did give me some scratches and bites recently. So the momentum is part of it. Basically, a higher energy neutrino does have more momentum. I don't want to, not acknowledge that. But I wanted to say that the main thing is that they're weakly interacting. Now, you're asking about how are they moving? Freely. They move freely. They have an initial momentum. They just keep on going forever and ever until they're stopped. I think that's just they're trying to tell you how many are going through. Are you joking? Oh, I see. Like they're just going through. Got it. Okay. You're joking. Okay. If a neutrino flies through your thumb and no one is... Oh, I see. What you are asking, what's holding them there? Nothing. They're just going through. I think the number you looked up, how many go through, that's just a way to say how many are... That's just a way to say how many there are going through some square centimeter. That's just to say that there are lots of them being made by the sun. So, if that makes sense. and okay, another thing that holds them a little bit is they do have some mass. So they do interact gravitationally, but their mass is very low. So I would say nothing is really holding them to the square centimeter. The going through part is just to talk about their flux. Oh, very nice, Raphael. So literally, it's just a way to denote their flux. But they do have a mass as well. So there's that as well. They do interact gravitationally, but low mass. I'm hearing the Queen song. Yeah, they are very out of control and care about nothing. Just like me. They're very out of control. Can't stop me now. Yes. Aw. You guys kept me up late. Any other questions? Any super chats? Super duper chats? Supernova chats? Thank you everybody for joining. Thank you so much. If you joined late, please do rewind and see the whole thing. We talked about neutron stars, pulsars, and then we've been chatting about neutrinos after a brief drama session as well. Sorry about any of the drama if you disliked it. I certainly don't like the drama. Watch that Fantastic Four movie. Thank you. Happy birthday once again to Raphael. So another reason why I don't watch the movies is because I don't have any streaming services right now. I've been so busy. And I take long walks and whatnot. So I don't really watch stuff online. Piracy, I don't really do piracy either. If you like neutrinos, yes, we can continue to talk about neutrinos tomorrow. In fact, maybe I'll prepare some notes and get some stuff out from my previous work on neutrinos. Let's do that. Adam says, I'll set an alarm to join tomorrow if you're on. Yes, please. Let's talk about neutrinos tomorrow. I was thinking what to do tomorrow exactly. YouTube, yeah, I do have YouTube. So I can watch it on YouTube. From the muon, yes, muon neutrino, yeah. How about tomorrow? We will cover the neutrino stuff in detail. Like we can introduce neutrinos and the different flavors and everything, and we can talk about that in detail tomorrow night. So yeah, set an alarm for a bit earlier. I'll try to get on by 11 or something tomorrow. 11 p.m. Eastern Standard Time. 11 p.m. Eastern Standard Time, yes. So, and Adam is from Canada, right? So you should be good. Yes, I used to do this Physics Friday sessions, and then Friday is usually very quiet. Like most people don't come, but I'm wondering, like, that might be fine. Like if only a few people come and you guys come, that might be honestly a good. Yeah, I'm in the same time zone. It might honestly be a good discussion, because sometimes when the few people who are here and very engaged with the content come, it can actually be a very good discussion. So tomorrow, why don't we do that? We can discuss neutrinos and do like a proper introduction. I can talk about my background and experiment and maybe show you the energy regime that I was talking about of the various experiments. Yes, we can do that tomorrow. That would be a good topic. That would be a good topic for tomorrow. Sometimes I branch out and do other topics that are not really like my exact expertise, because then I also get to learn. But neutrinos are what I focused on. Raphael says, I'm Canadian too. But Raphael, aren't you Swiss? There is people from all sorts of countries here. Thank you so much, everybody. Africa, America, North America, South America, Asia, Australasia, Europe, Antarctica, everybody, Madagascar, Oceania, Oceania. Everybody, thank you so much for coming. Thank you for joining. And good night and good day to you. And please do like, share, subscribe, and watch all our videos and shorts. And please leave your comments. That's always really lovely to see everybody chiming in and engaging with the content. Really helps the channel. It's still a very small channel, so I really appreciate everybody's help and support. Yes, the neutrino sun never sets. I love it. I love you guys so much. You are so you're so good at all this. You ask such great questions, and then you learn so fast, and you get it. We're vibing. It's a vibe. It's a vibe. We're vibing. The neutrino sun never sets. I love it. I love it. Thank you guys. Yay. Bye bye. Let me share it one more time and then go. My poor channel lost some subscribers today. Too bad and so sad. Please do like, share, subscribe. Bye.